Good afternoon. Welcome to the CERIAS Security Seminar from Purdue University. Today our speaker is Professor Apu Kapadia from Indiana University. His talk today is entitled Soundcomber, a stealthy and context-aware sound Trojan for smartphones. Apu?
Okay, thank you very much. Okay, right on schedule here. So I learned just now that this is actually a class and you get credit for it. So to get your credit, maybe you have to answer some questions. I don't know. I feel like I'll make this a little more interactive. So, feel free to interrupt me, right? And then if things get out of hand, I'll say, okay, slow down everybody. Let me just get through this thing. But let's try to keep this fun. Okay, so this talk today is about smartphones and what can go wrong and hopefully what can be done about it. So this should come as no surprise, right? The smartphones are pretty powerful computers in your pocket, right? And I suppose to many of you in this classroom, you might be thinking, well, duh, I mean, what's new? They're actually not quite powerful. But depending on who you talk to in the room, this might be a high-end machine, right? Probably Christina agrees with that. Maybe if there were some, older professors in the room, they'd be thinking of these as supercomputers, right? But the point is that these things have become pretty powerful. Dual core, 1.2 gigahertz processors, 1 gigabyte of RAM. Gosh, I'd have killed for a 1 gigabyte RAM machine back when I was a student. 32 gigs of storage, running Linux. I had to deal with really piddly OSs back in the day. So this is great. So this new landscape of computing excites me. Okay. But of course, this is just another computer, right? That's what I've been telling you the last minute or so. And of course, computers are infested with malware, right? Not very surprising. And so I just picked, 3 random news articles. Nothing special about these, but just quickly looking over them. There was some Android malware that stole information from 1 million users, right? There was some Trojan that was actually causing financial damage. It was sending, these premium rate SMS text messages, right? So somebody else was making money off of this, and it was causing you harm too. And then some security experts obviously created a very nice, rootkit. Once you've rooted an Android phone, you can install this nice rootkit and hide your actions and do all kinds of fun stuff. So none of this should be surprising, right? So we asked ourselves the question, is there something new to be done here? Can the bad folks, the attackers, actually go one step beyond these attacks that we've been expecting, right? And we started thinking, well, okay, what's so new about this computer? Well, it's different from a laptop. The laptop, we carry around in our backpacks. Maybe it is portable. We open it right now and we'll close it later. But the smartphone is always in your pocket, more or less, or your purse or your backpack. And it's always on, even if the screen doesn't show anything. It's in sleep state, but it can still do things. And it has these sensors, right? So we thought, well, this is new. Okay, we have a computing device with a whole bunch of sensors. It's with you everywhere you go. And what can we do with it? Maybe malware can do something new and interesting. Okay, so this is where we're coming from. Okay, we called it sensory malware, just to give it a cute name, right? So this is something new and interesting, we think. And okay, what are some examples? There's the camera on the phone, right? So now you have malware that can look in on you. Now, of course, the laptop can do the same thing, like I just mentioned. But the difference is that this phone is always with you, right? Many of you probably read this, take your phone to the restroom, right? Now imagine the camera taking a picture of you in the restroom, right? I mean, you can think of various scenarios. Or we don't use smartphones just for making phone calls. In fact, probably a lot of us don't make phone calls anymore. I hardly use my smartphone to make phone calls, but I'm always reading the news or sending email and text messaging and so on. So this phone is out in my hand a lot, okay? The camera looking at me and the camera in the back looking at whatever is in front of me. So malware sensory malware can do quite some damage with the camera. And I'll show you an example towards the end of this talk. There has been some existing work on this very attack that I'm mentioning. They talked about malware that can upload video. Now, of course, this is not very stealthy. Uploading megabytes and megabytes of video for processing somewhere on the back end is quite demanding. So it's not the greatest example of malware, but it is at least one reasonable example. There's the GPS, of course. So now malware can track you where you're going, build up some kind of behavioral profile about you, maybe share these profiles with advertisers. If one example is, if let's say this malware has taken over a whole bunch of phones, so now you can think in your minds, think of a cellular botnet, right? A mobile phone botnet with some bot master controlling these things. Let's say you've infiltrated phones of soldiers, okay? Now you can track their movements, right? And this gets pretty scary, if you're a military person. And so you can think of various attacks, both in terms of military or personal consumer privacy. Let's see, what are some other examples? And I encourage you to think of some examples, and I'll ask you to think of some in a second. The microphone, that's what this talk is going to focus on. We were very interested in the microphone. What can the microphone do? So this is what we started thinking about. Well, this is really cool. We have a phone in the pocket. It's listening to you all the time, wherever you go, all the intimate conversations you have. When you're telling somebody about how you hide your key under your flower pot, we could hear that and exploit that information, right? This is pretty cool, right? So I guess now my question to you is, just think about some interesting examples that you might try to overhear and exploit, and how would you go about actually detecting these situations on your phone. So think about it for, let's say, I'll just give you 30 seconds. Think about it, and then I want to hear some suggestions. What else can you steal if you had access to the microphone? What kind of interesting conversations might you steal? Any fun examples? Yeah.
You can listen in on conversations to, say, activate a credit card number. So you can get the credit card number, the security number, and the last 4 digits of someone's social.
Oh, very good. Okay. Well, we'll get to that in a second. So any other examples?
Part of the background conversation.
Like about what, for example?
I mean, yeah, I'm just saying something that might be important, but which is in the background. Probably you can pick that up too.
Okay, yeah, so you have no idea. So any conversation might have something juicy in it. Yep.
In the case of maybe a phone that was assigned by an employer, you can get proprietary information on something they're working on.
Yeah, very good. So yeah, trade secrets. When I worked in the government for just about a year, when you had these sensitive meetings, you'd have to leave your phones outside of the door for a reason, and this is one of those reasons. Okay, so good. So you've thought of some good examples. Now think about how malware on the phone might go about harnessing this information. How would this malware on the phone realize, oh, I've just captured a trade secret, right? How would you do that? Any thoughts?
Use some keywords.
Yeah, you could maybe do some keyword spotting. You can have some. Maybe you've targeted some particular types of conversations. But if you have, for example, a botnet of a million nodes, right? Now think about this problem in a little more general fashion, okay? You're the botnet master. You've got a million nodes out there. And now you want to collect as much interesting, juicy information as possible, right? And now you would have to try to target each individual situation, kind of load up this malware with keywords. You have to try to detect different types of situations where information might be revealed, right? So quickly we went down this route, exactly what you all have been suggesting, great suggestions. And we quickly started realizing, gosh, this is actually very difficult. I mean, how do we know that we've we've heard something interesting and juicy, right? We want to do this in an automatic fashion. And so we started constraining this problem space. So I encourage you to keep thinking along the lines that you've been thinking and think about how you might be able to detect these various situations. We picked one particular one, which is what I'm going to be talking about today, right? And this was already brought up by one of the students there. So we basically said, well, this one situation definitely is easy to recognize for us. Well, sort of easy, not completely easy. Is that we can recognize when somebody is revealing or about to reveal a credit card number. And usually a lot of people do this in the context of a phone call, which you make on smartphones usually now. And so that was interesting that we could definitely pick this out, and I'll explain how. And at the same time, the other advantage, let's see, I'm just trying to think of the other real advantage. It inflicts financial damage on the victim, right? In many of the other examples, the GPS example, I think we came up with some good examples of damage, but you could sometimes argue, well, how many people are really concerned about their location privacy and so on? Yes, you might, I'm actually quite concerned about location privacy, so maybe you can, maybe this malware can upload information about my location and maybe I'll be worried about it, but the general population may not care so much about, okay, fine, so these people know my location habits when I go to work and so on. But this was a very clear-cut example of damage that probably everybody would be worried about, right? You're losing financial information. And you could generalize this to bank information, and there you have real money involved, real money from your bank. With credit cards, the credit card company assumes some liability, but it's still a financial, it's still a pain, right? Because it's related to your finances, and it's a little more serious. So that's the reason why we kind of zoned in on this particular example, right? So you can see how this was easier to focus on, and the other ones, the more general problem is more challenging. So still plenty of future work to be done. Okay, so now that we've decided to go down this route, you always want to start with the naive approach and then try to figure out what's wrong with the naive approach, right? You shouldn't all of a sudden start trying to build something huge and complicated. So you first build a straw person solution and then try to see what's wrong with it and then try to improve. And if there's nothing wrong with it, you just stop and move on, right? So you want to make sure that you're doing something interesting. Okay, so the naive approach is malware on your phone that just records your phone calls and uploads it to the backend server, right? Just as an example, recording a minute of audio is approximately 100 kilobytes, plus minus. So I don't know, how many phone calls do you make in a day? How many people make 5 or so phone calls a day? Okay, just a few. How many people make more than that, or how many people make less than that? 5 or less. So basically, I'm getting the sense that it's 5 or less phone calls. So let's just go with 5, which is pretty convenient. That's the number I picked for this slide. So 5 phone calls. Let's say I record just a minute. I hope that I get your credit card within the first minute. When might this happen? I call up my credit card company for some reason or another every month or two, and it asks me to type in my credit card number. Once or twice a week, I get lazy and don't make my lunch. I order lunch over the phone. So Jimmy John's, here's my credit card number a lot. Yeah. I guess I'm sort of endorsing Jimmy John's, but I should also say I'm sick of Jimmy John's. Okay, so it goes both ways. So that cancels out the endorsement, right? Okay, no, they're good and fast. Okay, anyway. But they have only one vegetarian option. Oh, okay. Okay, so good and bad. Okay. All right, we're getting carried away. And so you can see how maybe once in a while, maybe once a month, once a week or so, the malware hears the credit card number right? And then sends it off to the back end, to the malware master, right? So you have a malware master who's controlling the botnet and is waiting for credit card numbers. Okay, so this might seem reasonable, but now, well, I just mentioned the botnet. Think about 1 million phones. Now all of a sudden you have this malware master hearing back from a 1 million phones, right? And actually, I got ahead a little bit about telling you that the phone is sending the credit card number. In this example, we're just uploading audio to the back end, and the malware master is doing the computation, the analysis on the audio. Okay, so the extraction of the credit card number, which is this gold brick, was done on the malware master's end. Now just imagine 1 million or so phones sending you terabytes of information. The malware master server is getting overloaded, lots of computation to be done. That's just too much work. Why would you do something like that, right? You want to be smarter. Okay, now I'll get back to that issue in a minute. There's another challenge, and that, not a challenge, there's another shortcoming of the naive approach, is that when you install an application on Android, it asks you, the operating system asks you, this application is requesting the following permissions, allow or deny, right? And in this particular example, the application is asking for network access and also recording audio. This is a dangerous combination, an application that records audio and can access the network, right? Now, what do you think most users will do when they see this screen? They'll probably say yes. Okay. So in some sense, you can say, well, the naive approach actually might work. Okay, it might work because, especially in context of this particular problem, it's not really going to be a problem. I'm telling you it's a problem. It looks suspicious, but most users click yes anyway. And that's a fair point. Okay, and this is a problem with our security systems in general, at least on end user systems, that people just click yes. And that's an ongoing challenge, and people continue to do research on making systems more usable and hence more secure, hopefully. But I want you to think as researchers, right? There are actually a lot of security solutions already out there that I'll outline very quickly towards the end that try to catch such combinations. So you can imagine a system like this, and there are prototypes of these types of systems, like the one I'm mentioning in the slide here, that on install time, so this is a particular system called Kirin. At install time, it can look at the permissions that your application is requesting and immediately say, this is unacceptable. You should not be able to install this application, too dangerous. Okay, so you'll have to at least buy that we're in research mode now. Okay, we're assuming that we have the most cutting edge defenses on the smartphone, and it will definitely disallow something like this. So we have to get around this challenge as well. Okay, our permissions need to look relatively innocuous. Okay, not only to the human but to automated checking tools. Okay, so quickly, our contributions are that we're gonna show you this malware called Soundcomber that does targeted and local extraction of valuable data. So it's local, that is, it's being done on the phone. So you're not overloading the servers at the malware master's end. And this analysis is targeted, and doing targeted analysis allows you to do it efficiently, right? You can't be analyzing hours of conversations. I mean, the smartphone not plugged into the wall, you'll quickly drain its battery, or this application will look suspicious. So you want to do targeted extraction. As a result, it'll be stealthy, hopefully, right? And so that's what we aim to do, to make this malware stealthy. And we want it to use inconspicuous permissions, right? Okay, so let's go back to that diagram I showed you where the malware master was completely overloaded by the computation and the storage. So we just push all that to the phones, right? And now instead of receiving terabytes of data, every once in a while when the malware kind of hears and recognizes a credit card number, it extracts it and sends it back. Okay, so This is just an animation showing every once in a while, a gold brick making its way to the malware master. How do we get around the permissions issue? Very easily. We actually create two colluding applications, okay? And I'll get to how we can have a realistic attack in a second. And now we have two applications that, when you look at their permissions combined, have dangerous permissions, but individually they don't have dangerous looking permissions. So the Soundcomber application on the left is only responsible for recording and extracting the credit card numbers, okay, from phone calls. And then you have a deliverer app that all it does is it has network access and can send the information to the malware master. Okay. Another thing to keep in mind is that these two are Trojan applications. You have not compromised the operating system. This is not, an attack on the OS itself. It's just these are apps you sell in the marketplace, quote unquote legitimately. Right? It could be, you could have a voice memo application. Like people download voice memo apps, for example, and that obviously has to have access to the microphone, right? So it's legitimate to have these Trojan. Well, a Trojan can very easily mask itself in one of these legitimate-looking applications, and then, if the deliverer Trojan app only needs network access, well, pretty much, a large fraction of apps accesses the network probably, right? You can imagine. You might download some new kind of browser or, some Yelp application or some food, restaurant recommendation application and accesses the network, right? Okay, so you have these two, we split it up. We split up the single Trojan into two, okay? And then they're going to communicate over using a covert channel, and I'll talk a little bit more about that. The reason why we use a covert channel is because, again, there are very simple defenses to kind of prevent two applications from talking to each other, especially if the combination of their permissions is dangerous, right? So very simply, the Soundcomber app is only responsible for the analysis and extraction, and then the communication component of both Soundcomber and deliverer apps handle the covert communication and then sends it off. Deliverer sends it off, okay? Now let's take a closer look at the permissions business. So here's here's the naive permissions that you would have, right? You would have network access, you would have record audio. The other permission to keep in mind is that our app needs to know when you're calling a credit card company, right? If it's going to extract the credit card number, it needs to know when you're calling the credit card company. So this animation is going to try to focus on that one piece. If you just start out with the naive approach, you would request intercept outgoing calls and read phone state and identity. Many apps read phone state and identity because, for example, you don't want your app disturbing the user when the user is in a call, right? So that's not innocuous, but that is innocuous. But intercept outgoing calls is kind of a scary permission. Okay, why would you have an app that intercepts outgoing calls? Well, if you intercept an outgoing call, then you can figure out what number is being called. So the malware can say, "Oh, you're calling Citibank. I'm going to record your call and then extract the credit card number." So if the first animation just shows removing the network communication. We can do that by splitting up the apps, right? What you can do is, if you don't want to intercept outgoing calls, you have another option, which is arguably, less scary, okay? Which is you read phone state and identity. Like I said, that's very common. And then you read contact data. Okay, now, read contact data. The downside with this approach is that now you can only figure out, by you I mean Soundcomber, can only figure out which number was called after the call ends. You can think of this as going into your recent call list, right? So with this permission of read contact data, you can look at your recent call list. So can you think of any applications that might use let's make the question more specific. Let's say we're thinking of a voice memo app, right? This is the Trojan we're trying to sell Soundcomber under. Why would a voice memo app need to read your contact data? Can you justify it in any way? Yeah, very good. So you might want to tag people in it. Any other ideas? I don't know, maybe you want to share voice memos with somebody and mail it to them. So, you can think of some situations where you might want a voice memo app to have it. But we wanted to remove that as well, to say, well, let's try to make it even less suspicious. And so we finally ended up with just these two permissions, okay? Record audio, which we definitely need, and read phone state and identity, which we argue is just very common anyway. And I'll tell you in a second how we end up figuring out what number you've called. And I've been talking about the voice memo app over and over again, but we also found, for example, a wake up alarm application where you can record your own voice, right? Or your girlfriend, boyfriend's voice or something like that to tell you to wake up. Or your parents' voice, nagging you to wake up. That'll probably work better. So you can easily imagine applications like this on the Android marketplace. Now, how do we find out what number has been called? Right now, you have malware that now has to analyze all your phone calls because it doesn't know what number you've called. So we have this step called hotline detection, okay, which basically tries to figure out, just by analyzing the first 10 seconds or so. I'll get into a little more detail, but it analyzes Soundcomber analyzes the first 5 to 10 seconds, basically listening for welcome to Citibank or whatever, your favorite bank, or welcome to Bank of America, right? These phone menu systems say the exact same thing in the exact same voice, right? So you can just listen for these things. You can imagine the malware has like a little database of greetings that it can compare against, right? And we're talking about a botnet of about 1 million nodes or so. It's okay if you get it wrong sometimes. It's okay if you only target the top 5 banks. So you don't have to try to recognize every single bank in the world, right? And so you can imagine, say, Soundcomber just targets the top 5. And just by listening to the greeting in the first 5 seconds or so, you figure out which bank, whether the user is talking to a bank at all or talking to Jimmy John's or whatever. Although I haven't encountered an automated ordering system at Jimmy John's, so that would be a little harder. And then you can start recording. You can analyze the audio even, you can fully analyze the audio once you've detected that a sensitive number has been called. Okay, the part that I haven't talked about but have been hinting at for a while is, separating out the two applications, but how would you go about doing that? So we thought about this, okay, you might get one Trojan onto someone's phone, but what's the likelihood that you're going to get both the voice memo Trojan and some other Trojan with network access both onto the phone? And yes, sure, getting two Trojan apps on the phone is going to be more challenging than getting one. So we tried to think of a couple of ideas. One idea would be to have pop-up ads, or trying to continuously advertise some application that sounds very enticing. Maybe 1 in 100 people will install it. So that'll work, but you'll probably not have a high success rate, as high as you may want. The other approach we found was a packaged app. Okay, now we didn't do a user study, but at least what we found is you can have an app within an app. You can, while installing an app, during the installation process, the application can say, well, we need to install another helper application. Is that okay? Right? And it turns out you can actually you can actually install an app from within an app like that. And we kind of argue that, okay, this is going to be a lot easier if you convince the user that this helper application is needed. So here, those are two possible approaches. there's been some analysis, and I'll talk about this a little later, a paper that's going to appear at NDSS by some other authors that really takes this attack seriously and justifies it even better than I did right now, but through a numerical analysis of how many, malicious apps are on the Android marketplace and how this is very realistic. So I'll talk about that a little later. But in general, we found two reasonable ways to get the colluding Trojan apps onto the same device.
So that's the one from NC State?
No, I think this is from Europe. Okay. Okay, so let me go into some details about a closer view at how some of the extraction is taking place. So once Soundcomber has permission to access your microphone, it can record your calls, right? And these are the raw bits right now. So the recording component is getting the raw bits, and then we have a processing step. We use some pretty standard, tools for processing because we're not signal processing people. I'm sure you can do even better than what we did if you could tinker around with the algorithms. But essentially, we do tone-based detection and speech-based detection, right? So we're going to try to detect even spoken input of credit card numbers. Some of you may have spoken your credit card. Some of you may have typed it in. Some of you may have done both, right? Type in some tones to navigate the menu, then you might say your credit card. We wanted to try to capture, all of these or most of these situations. So we do, two types of analysis. We first extract the tones, and we also do the speech recognition on digits. And since we're only focused on digits, you can do this quite feasibly on a mobile phone with local analysis, right? If we were trying to recognize the entire spoken English language, it would be more computationally intensive. But we have a fixed dictionary of digits, so we can do a little more. We can analyze the data a little more efficiently, well, a lot more efficiently. And then the credit card number is extracted in the next step, and sent to the deliverer app and onto the malware master. But it uses something called a profile database, which I'll talk about on the next slide. Okay, what is this profile database? To do a little more targeted extraction, both for improving your success rate at pulling out sensitive information and to reduce your computation. So you can think of the profile as essentially a state machine of the Hotline menu system, right? When you press 1, what are the next menu options that you get? In this example, you type in 1 or 2. If you type in 1, it might prompt you for your account number, and then you type in your account number, then it asks you for your PIN number, right? Or you might type in number 2, and it's a menu related to loan and credit card information, but you might still type in 2 after that, and then it might ask you for your credit card information, and after you type in 1, in this example, you navigate to the point after typing 2 to 1 to the point where it asks you to enter your credit card information, right? So the IVR system might say, are you calling about loans or credit cards, right? Press 2, and then so on. So you can imagine Soundcomber has a profile database, right, of the top 5 banks, 10 banks, how many ever banks you want, and knows the state machine transition diagram, the state transition diagram of the phone menu systems. Now, if you know that, you know where to look in this in the speech transcript. Where to pull out the numbers, right? You could follow the state machine by looking at the tones the person is typing in, and so on. So, just a little bit more about tones. You might already be aware that when you hit a tone, when you push a button, you hear this kind of frequency, this tone, the sound. It's not actually a single frequency, it's actually a dual frequency tone. Okay, so that's why they're called DTMF, which is dual tone multi-frequency signaling. So there are 8 different frequencies, right? And if you, for example, punch in a 9, the phone plays two tones, 2 frequencies, 852 hertz and 1477 hertz. Okay. I don't know how many of you are aware of this, but so that's what happens. Now there was an additional challenge, okay? Soundcomber, when it was recording phone calls, couldn't actually hear these tones. Right? So it turns out that the phone is just playing this back to you, because as humans we expect to hear these sounds, but these tones are actually sent over some kind of signaling channel to the cellular phone company that then will play the tone into the regular call. It's just a technicality. So, is it game over? Well, no, it wasn't game over, because it turned out, and this is not surprising, but it turns out that the microphone can hear the tones being played to the user. Right? It's being played through the earpiece, right, for you, but the microphone can pick it up faintly. Okay, and that's what we exploited. So you can think of this, it's a side channel, right? They're not intending for you to be able to pick up the tones, but you could pick it up anyway. And so it was a little more challenging. These tones are designed to be detected, but since we had to pick it up through a side channel, they were actually very faint. So it turned out to be challenging up to a point to pick up these tones. So this is some of the additional work that we had to do. And so there's a standard algorithm that's used for picking up these tones. The only different thing we needed to do was adjusting the thresholds. Okay, because normally the tone is played out really loudly, but now these are so faint that you're not going to detect these tones. So you're going to have to set the threshold so that you don't have, so that you can detect the tones, you don't have false negatives, you don't have false positives, right? And how do you do that? And what we found was that you can basically figure out what the average energy is for that particular frequency, right, throughout the transcript, and then set some factor above that. If the tone exceeds twice the average, then register it as a tone. Okay, if the energy exceeds twice the average, that's just something we found that worked in our experiments. So there's some dynamic thresholding over there. Okay, so that was tone and speech detection. The speech detection is pretty standard, like I mentioned earlier. So by now, hopefully you're convinced that Soundcomber can figure out what number you're calling, use the state machine, use the recorded audio to extract the audio. Now we have to Soundcomber has to actually send it off to the deliverer app, right? Deliverer. And how do you do that? So we used covert channels for that. Now, a covert channel is a channel that was not intended to be used for communication. You're trying to isolate applications. They should not be able to talk to each other. But nevertheless, your application finds some way to talk. Your applications find some way to communicate, right? So those are called covert channels. Covert channels we've known about this for a long, long time. So we just thought, well, we could probably use one of these standard covert channels because Android doesn't really have any defenses even against the standard covert channels. But we tried to push it a little more to see, are there any interesting covert channels that did not exist before, that are inherent to the Android middleware or operating system that would be actually hard to get rid of because of the way Android is trying to provide functionality. So we found some fun ways to do it. I guess I'll talk about the first crazy, ridiculous way that nobody should ever use. But we found, and we actually built this and it worked. This was just a few hour diversion on our part. But basically you can have one application vibrating the phone and the other application picking up the vibrations through the accelerometer, right? So you have this phone signaling zeros and ones by vibrating or not vibrating, and you can imagine your phone kind of dancing around on your desk with these vibrations. Yeah. So we actually did this for fun. We need to have some fun sometimes, right? But this is not something you would want to use. It is a covert channel, but it is a very very visible to the user kind of covert channel. So it gets the job done, but it would be detected. But in any case, while playing around with this vibration business, right, we realized that, okay, you can actually change the vibration settings of the phone, right? You change your phone from whatever volume setting to vibrate, and that broadcasts a message. The Android system then broadcasts a message to other applications saying the phone has been turned to vibrate. Okay, so this can be turned into a communication channel, right? Soundcomber can turn vibrate on off, and the deliverer app can try to listen for this at some pre-specified time, right, at 1 a.m. when the phone is charging. The volume settings didn't have this broadcast mechanism. You can change the volume settings. An application like Soundcomber can change volume settings, but the deliverer app won't be notified. So you can kind of set volume settings, and then the deliverer app can poll and check what the settings are. The screen setting covert channel was interesting. You could turn the screen on and off. Now you would think that this is quite visible, right? Your phone's like the screen's going on and off to signal zeros and ones, and the deliverer app kind of is getting these settings, whether the screen is on and off. It turns out if you turn the phone on and off, the screen on and off quickly enough, the information gets conveyed, right? That the screen has been turned on and off, but it's not visible. Okay, so maybe there's something in the Android OS that says that the settings should not have changed in the last some number of milliseconds. Then actually go ahead and change the screen state, physically. So it turns out that you can actually mess around with the screen settings to actually communicate between apps. And then the file locks at the end is a standard covert channel that's been known, that we've known about for a long time, and you get a high bit rate. You could probably use some existing defense for that. But for the first three, it would be challenging, right? Because the Android system is providing these services for a reason, so that other apps can make decisions based on the volume settings and so on. And how, what would you do about it? In the interest of time, since I sort of already explained what these different covert channels are doing, this is just a more pictorial representation, a little more details. I'll just go over it very quickly. The volume settings, like I said. The only thing I'll point out is, like I said, the deliver application over here. Let's see if I can get my mouse. Can't. Okay. The deliver app checks the audio setting, but the volume can be set to 7 different levels. So you can transmit 3 bits at a time. Right? It's not an on-off channel like the vibration setting. Now what I wanted to show you was a quick video demo. Let's just go ahead and do it to show you that we actually built this thing, and I'll show you we actually call Citibank or some bank, and we hang up the phone pretty quickly, so we don't cause any damage, right? But we placed one real call just to make this demo. So this is the wake-up call alarm application that uses way more permissions than our Soundcomber app. Just speed that up a little bit. I think we get the idea about that aspect. So this demo is showing how you can steal the speech-based input, right? Credit card number that's input using speech. Wonder if I can.
For regular customer service on your credit card, press or say 1.
1.
Welcome to CitiCard. To expedite the handling of your call, please touch tone or speak your 16-digit account number now.
4 2 0 0 7 1 9
So we
3
can detect the Chinese accent as
0
well.
9 3 9 1 4 0 7.
Sorry, I didn't understand.
So what's funny is Citibank didn't really get it, but Soundcomber picked up all the digits. So this is the malware master server in Switzerland. Okay, waiting to hear back from the phone. So it takes about 10 to 12 seconds to do the speech analysis. The covert transfer took about 3 seconds, and then it got to the server. Of course, I can't show that happening, but I just labeled the times appropriately. Again, in the interest of time, I'll just stop here, but the stealing tones is basically the same thing with, tones being typed in. Okay, so the remaining time, at least let me give you some, performance numbers. You should think of this as, preliminary analysis. Okay, we had 60 speech recordings from 3 speakers, international speakers, it turned out. And so we had 20 from each. And we had, them, simulate phone calls. We didn't really want to call Citibank or some other bank so many times and abuse their resources. And so we just recorded these simulated phone calls. And then similarly, we collected tone entries. And then we ran our analysis to see, well, how often can our speech recognition, follow the state machine, get the real credit card number, and so on. So with no error, right, we got all the 16 digits of the credit card number. We got that 55% of the times. With one error or one missing, right, so one digit was wrong or one digit was missing, we only got 15 digits. With all those combined, we succeeded 75% of the time, which we argue is not bad at all. Think again. To change your perspective from attacking one machine or one phone to millions of a million or so size botnet. So instead of getting 10,000, 20,000 credit card numbers, maybe you got 75% of that, right? We think that's still okay. There is room for improvement, but it's okay. For tones, we were able to get 85% with no error, and all of them pretty much with only one missing or one error. In terms of how much time it took, our speech recordings were about 20 seconds. Our tone recordings were about 45 seconds. In either case, the processing time was 7 or 8 seconds. So this is not bad. You can imagine maybe doing this processing in one shot for 7 or 8 seconds, the phone slows down, or you can split up this processing, just do a little bit over several minutes, or you can do it at night when the phone is charging. So it should not be very detectable. We did the hotline fingerprinting. We fingerprinted 5 different hotlines. Like I said, we thought it was justifiable to just target the top 5 banks. We also recorded some samples of normal conversation, right? Because you want Soundcomber to differentiate between a hotline and conversation, and additionally figure out which particular hotline you call. So 55% of the hotlines were correctly detected. If we were talking about a single attack, again, 55 is not a great number, 55%. But from our perspective, from this huge botnet, we thought that was also more than enough. 40% of the remaining 45%, most of them were missed. We couldn't figure out, what. Soundcomber didn't even know that you're making a call to a hotline, and 5% of the time it said it resulted in an incorrect hotline identification. Okay, it said, this is Bank of America, for example, and it was really Citibank. It detected conversations pretty well. So if you're having a conversation, it knew you were having a conversation. Okay, so I'm wrapping up the Soundcomber stuff now, and I have about 48 seconds left. Maybe if you hang around more, I'll tell you some more interesting stuff. But you can think of improving Soundcomber. You can defer throttle processing. I talked about that. You can kind of check the user's presence, and you might be able to think of better performance enhancements to our analysis. We actually did come up with a defense that recognizes, when you're not making a sensitive call, and when you make a sensitive call, it disables the recording of the audio. So our reference monitor disables recording. There has been recent work, following up on this general line, stealing your keystrokes by using the accelerometer. If you keep your phone next to your computer, it might be able to read the vibrations. There was work on video. I'm out of time. I found just recently, in the last couple of days, I found a paper that is follow-up work in the defensive line to be presented at NDSS in a few months, and they actually try to defend against the Soundcomber attack specifically. And they do a really good job of characterizing all the related work so far on Android security. I thought I would have more time to describe this slide, but essentially, I encourage you to look at this paper. It's a very good resource if you're curious about all these different mechanisms. But they very conveniently for me point out, but they do not prevent the Soundcomber-like attack because of this or that. But then their system does. Okay, they specifically designed the system called Xmandroid to detect these covert channels that we were using in the Android's intercomponent communication framework. Okay, that's something to look at. So in summary, right, sensory malware we believe is a real threat. We need to explore other such threats, still more fun to be had, like this accelerometer paper and the video paper. We did some audio. We talked at the beginning about how this is just a preliminary attack using audio. We want to try to target more general situations. And how do you do that with local processing? And then how do you build generalized defenses? Even the paper I just mentioned might solve the Soundcomber problem, but these types of malware could just try to figure out some other kind of covert channels. So there are plenty of challenges left in securing smartphones. So I'll stop there, and then I guess I'll take questions. We have 10 minutes or so for questions. Yep.
Have you looked at Apple smartphones, or have you limited your research?
We limited it to Android just because, as from a development perspective, it was a lot easier for us to mess around at the OS level and install like these speech recognition libraries. It was just a lot easier from a development perspective to work on Android. And from our perspective, we just wanted to build this proof of concept. Right? So now that you see something like this, it's not such a big leap to imagine similar functionality on different OSs. Although you can argue, well, how easy is it going to be to install these paired Trojan applications through the App Store, through Apple's App Store? How do these folks on the back end approve applications? Are they actually looking into security stuff? They're interesting questions. There are applications downloaded through the App Store more secure? Any opinions? How many people think it's more secure? How many people think it's less secure? How many of you think that downloading an app from the Apple App Store, which is centralized control, somebody is going through and vetting your applications, right? If you install an application through that route versus the Android app market, where anybody can upload their new app pretty much without any centralized management or checking to see what is your app doing, right? You have these two models. Which model do you think is more secure? Which model will prevent malware such as this more effectively? Any opinions? I don't think there's a right or wrong answer. There's just opinions to be had here. Yeah, Ningui?
Yeah, I think from what I've heard from the kind of survey work on smartphone and app, the Apple model is more secure because it has some deterrence effect. Not because people can actually find the malware when they're looking at the code, but because people felt that they could be caught.
Right, and the consequences that then you lose your developer's license.
There's some kind of connection. I actually don't know if you want to become an Apple developer, you need to give enough information for them to trace back to you. If that is the case, then certainly that is a determinant factor. Yeah,
and then you can think of maybe signing up with different credit card numbers that you got through Soundcomber. Maybe, you can think of signing up under different identities and getting back into the App Store every time you're banned. This is similar to the Sybil attacks, if you're familiar with that. where you can just come back with another identity if one of your identities gets blacklisted. Now, are people in the Apple App Store actually looking into the security, or are they looking into the general user experience, right? I mean, I know that they're very interested in the user experience to make sure that these apps work well as advertised and so on. But, if they're going to check for security, then, if they have the right tools, they could do that, and that arguably would be more secure. I don't know what they're doing in terms of security at the back end, but you could, in that model, possibly, at least it's my opinion, end up more secure if they are actually checking for these things. Yeah.
Regarding separating apps into two parts, so that they pass the Kyrian test or similar kind of test. I mean, the Kyrian, as far as my understanding goes, it's just a language to specify sets of permissions. So you can simply add more permission sets to it, or what you could do is to install two apps. What the technique you're using is installing another app from an existing app.
Right.
So you can combine both their permissions and check if one app.
You're right. Yes.
So that way of separating our permissions into two different applications and then trying to install both of them, it doesn't look so sophisticated enough. I mean, it can be easily.
Yeah, I agree. That's a good point. I mean, we circumvented the existing defense, but you can think of ways to now improve Kyrian or whatever, many of these different defensive architectures to say, well, make sure you do a better analysis of this app, see if there's an app embedded in there, combine their permissions, check if, so the packaged app would suffer from that. Now, in terms of the more challenging one would be the ads that come in, right? Like if you're advertising to the user, hey, check, see, do you want to install this application? So that you might not be able to do while installing the original app, but you could certainly capture an event that you could have Kyrian or some similar system kind of recognize that you're installing another app and it was induced by this other app, so let me analyze these permissions together. So I think you could defend against those two scenarios. And then you would now have to rely on colluding apps, just hopefully two of these apps being installed through the app market. So, the malicious folks would have to think of two really cool applications. So yeah, that is a challenge. So definitely it's not as easy as just getting one app on there. So yeah, good point. Any other thoughts? Yep.
Have you tried running tests with interference or background noise for Soundcomber on calls?
No. The short answer is no. It was, we basically did this in a lab setting, essentially. For example, in someone's office, right? And the reason why we felt somewhat justified in doing that was, when somebody is revealing a credit card number on the phone, they'll usually go to a private space. So we kind of thought that was justifiable, that, I would normally go into my office or shut my door when I'm, revealing my credit card number. So yeah, so we thought it was reasonable to assume a somewhat quiet environment. But we didn't actually test out noisy situations. Can any of you think of cool ideas for sensory malware beyond audio? Well, let me know if you think of any, or go write a paper yourself. Because I think there's a lot of fun to be had here, basically. But just a general note: you want to always, rise above the previous attack. So if it's just another attack, maybe it's not so exciting, right? You would want to think of some attack that still. Now that we know about Soundcomber, now that we know about the spy phone, which was the stealing keystrokes using the accelerometer, now that we know about these couple of things, is there another attack that's even more interesting and exciting and surprising that was not an obvious extension of that? That's what you probably want to be thinking about, not yet another sensory malware attack. Just something to think about. Okay, I think I'll stop there then. Thank you.